This is Mrs. O'Neill for Chapter 13, Section 3, Factors Affecting Solubility. In this section, you will recite the major factors affecting solubility, or at least hopefully you can by the end. You're going to state the nature of the solute and solvent. That determines the kinds of IMFs among the solute and solvent particles are strongly influenced by the solubility. Know that temperature also affects solubility, which we mentioned before, and we want to remember that most solids are more soluble, whereas gases are less soluble at higher temperature. So we're going to look at soda actually today. Recognize that solubility of gases increases with increasing pressure. So again, pause, fill in your notes, and then play to hear my words. We've mentioned before, like dissolves like. What does that mean? Well, polar solute will dissolve in a polar solvent. A nonpolar solute will dissolve in a nonpolar solvent. However, polar will not dissolve in a nonpolar, or vice versa. So they just do not mix. So the three factors that determine like dissolves like, what's going to happen is the structures, the pressure, and the temperature. So let's understand like dissolves like. So let's look at some structures here. So water soluble molecules must have a dipole part of their molecule, right? So in other words, they have to be polar bonds, right? If water is going to dissolve a solute, that solute has to be a dipole or a polar molecule. To be soluble in a nonpolar solvent, then the molecules must be nonpolar. That kind of makes sense. Well, let's look at two vitamins. Let's look at vitamin A and vitamin C. Let's look at their structures. So here we have vitamin A, kind of got almost like that benzene ring, but it's not really, right? And then you have your double bonds, and ooh, look over here. You have one OH. So that's the polarity right there, just one OH. However, if we look down here at vitamin C, we have 1, 2, 3, 4. Ooh, we have 4 OH. Well, if we look at these two molecules and I ask you which one is more polar, hopefully you can decide that the vitamin C is going to be much more polar because of all those OH ends. Well, so what does this mean? When you take vitamin A, your fat actually is absorbing these vitamin A molecules because they are more nonpolar. Well, if it's more nonpolar and it's being absorbed by your fat cells in your body, that means there could be a buildup. The fat in your body is absorbing these vitamin A's, and it's kind of keeping it there. It's kind of absorbing it. However, you know that you are mostly made out of water. So when we take vitamin C, that's kind of why they say when you're not feeling well, take as much vitamin C as you want. Why? Because the vitamin C has all these OH polar ends that are going to dissolve in all that water that you're made up of, and it's going to be excreted by the body. Your body's going to get rid of it because it's going to dissolve in the water that you have. So that's why they say there's certain vitamins that you want to be careful how much you take because they're going to be absorbed by your body and your fat cells and stay there, kind of a buildup. And then there's some vitamins that it doesn't matter how much you take, you're going to take your vitamin C and it's going to leave right away. So you might want to take vitamin C maybe 2 or 3 times throughout the day because it's getting excreted right away. So we call water-fearing particles or materials hydrophobic. Makes sense, right? If you're fear of anything, you have that phobic, and water is hydro, so hydrophobic is water fearing. And if you love water, that's called hydrophilic. Just two terms that sometimes are talked about. So let's look at salt. Let's look at soap. Let's look at soap as an example. And we're going to use this as an example because what does soap do? Well, soap cleans things. But this is a molecule of soap. Notice it has like two parts to it. It has this your organic part of CH2s and CH3 here at the end. And then you have this phosphorus with all these oxygen surrounding it. So you kind of have two ends to soap. So you have this long chain. This is going to be your hydrophobic end, right? Because that's your nonpolar. It's not going to like the water. But here, because of this O, a lot of this is going to become polar, right? You have that negative end. You have a dipole moment here, and that's going to be your hydrophilic polar end. Well, let's draw it like this, just to make things a little bit easier when I'm going to show you these next couple of slides. So here's our soap. We have our nonpolar end and our polar end. Okay. So what does soap do? Like we said, washes things. Well, this is a nice picture of water, and this green circle in the middle is a drop of grease. So we're going to have that drop of grease in the water. And as you know, grease and water don't mix because grease is nonpolar and your water is polar. So we have a nonpolar and a polar substance. It's going to be immiscible. It's not going to mix. It's not going to form a solution. So that's what I just said. Grease is nonpolar. Water is polar. So how does soap help you dissolve that nonpolar in the polar substance? Well, this is what happens. Soap is going to grab the non-polar end of your soap, is going to grab that grease, and the polar part of the soap is going to help dissolve it into the water. So we have the non-polar ends is going to dissolve your grease, non-polar organic substances like food. Most of your food is non-polar organic. And here at the ends is going to be your polar part that's going to help dissolve in the water. So you can kind of imagine it like this. Now you have multiple grease spots in your water, right? And these water molecules are all going to be surrounded by the grease, right? But what's happening here is all of those little grease particles are going to be helping, that the soap is going to be helping dissolve that grease particle and then dissolving it into the water. And that's why they say, I forget if it's Palmolive or Dove or one of those says, it helps grease get out of your way. But so that's what's happening. Soap actually has two parts to it. It has a nonpolar and a polar end. So we always want to remember like dissolves like in that way. Read over this, see if you can come up with some kind of answer, and then play to see the answer. There's our glucose. What do you notice about that? A lot of OHs. So we have lots of polarity. Here we have that cyclohexene. I don't know about you, but I don't see any OH groups. So this is going to be more nonpolar. And read over that, and hopefully that makes sense. So what about pressure? Well, pressure has little effect on solids and liquids, and that should make sense because you can't compress them together, right? We never talked about pressure when we talked about solids and liquids. Gases, on the other hand, pressure really affects the pressure of gases. So as we increase the pressure, we're going to increase the solubility. In other words, if we increase the pressure on a gas, we're going to actually help it dissolve more. We're going to get more towards that supersaturated solution with that gas in the liquid. So let's look at soda. So the dissolved gas is really at equilibrium with the gas above the liquid, right? We talked about vapor pressure before. So here we have a bottle of soda and we have some CO2 that's being dissolved in that water. Well, how does that happen? Well, gas at equilibrium will dissolve gas in the solution. So we have here a dynamic equilibrium, right? We have everything is settled. We have our liquid. We have our particles going up and down at the same rate, right? We have particles from the liquid turning into gas at the same rate that these gas particles are coming back down. Remember, it's a closed system, so it's a dynamic equilibrium. So if we increase the pressure, so if we decrease the volume or increase the pressure, we're going to make those molecules dissolve faster. More of those molecules are going to get into the solution. Now we've disturbed the equilibrium, and that's okay because eventually the equilibrium comes back. But now if you notice, there's a heck of a lot more dissolved gas in that liquid. There's not as much gas up top, right? So the vapor pressure also has changed, right? So the stronger the attraction of the two, the stronger attraction between those gas particles and the liquid, the higher we can make this constant. And this is called Henry's law. We're not going to worry about it too much. It's not on your reference sheet, but that's what Henry's law is telling us. How much of this gas can we actually dissolve in our liquid? So now let's think about that soda. So when the cap is on, right, the fizz or the dissolved gas that's in the liquid is under a lot of pressure. That's how they get all the CO2 in here, because they actually put the CO2, they dissolve it, but they make it under pressure, right? And of course they still have to keep a little bit of space up there because of the vapor pressure. But when we open that cap, the pressure is released, right? We lowered the pressure because now this gas is escaping the liquid. And so as we lower the pressure, right, we have all of these gases gas particles were saying, oh, let's get out of here. So as these gas particles come out, so are the gas particles in the liquid are going to also escape. So we've lowered the pressure, and now we have all of this gas escaping. And so that's why if you think about soda and you don't want to shake it before you open up the bottle, that's because soda is under extreme amount of pressure because of all the gas particles that they got in there for that CO2. And that's one of the reasons why you can uncap, pour a little soda out, cap it again, and you still have a lot of bubbling in there the next time you open it, and then the next time you open it, and then the next time you open it, right? So you can open that soda bottle multiple times and still get that fizzing because they've put so much CO2 gas in there. They've dissolved so much in there because it's under extreme amount of pressure. So if the partial pressure of a gas over solution is doubled, how has the concentration of gas in the solution changed, again, after the equilibrium has been restored? So we have equilibrium, we've increased the pressure, so we have more dissolved CO2 is going to dissolve. Now the equilibrium is restored. So look at here, we got 3 particles, here we have 6. So it doubled, okay? So as we increase that pressure, we're going to also increase the concentration. So again, Henry's law, read over it, should make sense to you now. You just really need to understand that concept. Temperature, on the other hand, affects solids and gases differently. For temperature, increasing the temperature increases the rate at which the solid will actually dissolve, but we really can't predict how much that is except from a graph. And I'm going to show you that in a moment. For temperature of gases, however, as we increase the temperature, solubility decreases. All right, so those gas molecules can move fast and they're going to escape. So give this some thought and see if you can come up with an answer. Hopefully that makes sense. So here's that graph I was talking to you about. So every one of these lines, okay, these are all ionic compounds, or I should say most of them are ionic compounds. And as you see that straight line, those are your line of equilibrium. In other words, that's your saturation line. So any amount underneath that line would be unsaturated. On the line is equilibrium, and anything above it would be supersaturated. So that's what I have here. Again, I show you here with the NaNO3, the sodium nitrate, anything on that line. So if I were to dissolve, let's see here, 30, let's see here, about 90, I don't know, let's say 94 grams of NaNO3 in 30-degree temperature, 100 milliliters of water, 30-degree temperature, that would be the saturation line. So until I get to that 94 grams, that would be unsaturated. 94 grams would be saturated. And then if I can dissolve anything else in there, that would be considered a supersaturated line. So the big thing to notice here is your solids are your straight lines and your gases are your dashed lines. Look at your gases. As we dissolve, we actually dissolve less as we increase our gas. So it's the opposites of solids, which is kind of weird. But yes, as we increase the temperature of gases in water, we are going to decrease the amount that's in there. And that somewhat should make sense because those gases really just want to escape, right? Think about that. As we increase the temperature of water, anything that we dissolve in there is going to want to try to get out. See you in class.